Good afternoon, everyone. Am I audible and can you see the presentation? Okay. Okay, fine. So let us continue. So in last lecture, we were discussing about safe state. So whenever a process requests the available resource, system must decide if we can the resource or not, and that will be decided depending upon this safe state. Okay. Now safe state is actually sequence of execution. For example, there are n processes P1, P2, P3, Pn. Okay, so these are all of the processes in the system, and then if we can satisfy the resource request, of course, by any process Pi, okay, looking at the whatever the currently available resources plus whatever the resources held by other processes, say for example Pj, where this Pj is less than L. So that is basically, so for example, if in set sequence, if I am talking about say P of 5, then whoever is coming in that sequence before P5, if we can satisfy the request, then it is called as system is in safe state. Now meaning of this is very simple actually, even though in mathematical writing it seems somewhat difficult, it is not like that. Meaning of this is very simple. In layman's language I can say we can grant the resource to the process Pi if and only if still we can continue execution of all the processes. Maybe in a particular sequence, may not be like P1, P2, P3 is not possible, but maybe something like P1, P3 and then P2. Any whichever sequence, and most of the time we can have multiple sequences also. Okay, but if there is at least one sequence, okay, which will put your operating system in safe state, right? So now the same thing is mentioned there. For example, if Pi resource needs are not immediately available, then Pi can wait until Pj have finished. As I mentioned, even though P2 is arrived before P3, because of lack of resources, if P2 has to wait for the completion of P3, wait. Only thing is P2 will come later, say for example after P3, so that this sequence will be executed. So sequence of execution, if that exists, then the system is in safe state. Okay, so if the resources are not immediately available, no issues. Process will wait for others, and once that other process has finished, that will release the resources. The same thing is mentioned there. When Pj is finished, Pi can obtain needed resources. So for example, if P2 is waiting for P3 to complete, so once P3 is completed, then whatever the resources are there, they will be released. And once they are released, P2 will obtain those needed resources. They will execute and return the allocated resources back. That is the releasing of resources, and then this process will be terminated. Whenever any Pi gets terminated, P of I plus 1 can obtain the needed resources and so on. So that is what the safe state of system is. That there should exist a sequence of execution in such a way that operating system will make progress towards execution of all the processes. That is what the safe state. Now, depending upon the safe state, like we mentioned about whether there is a loop in resource allocation graph, and if there are only single resources, that results into deadlock. Similarly, if system is in safe state, there is no deadlock, and if system is in unsafe state, then there is a possibility of deadlock. Now whatever we see is deadlock prevention. Now we need to see about like deadlock avoidance. Now deadlock avoidance will ensure that system will never enter an unsafe state. That means if any process needs resource and allocating that resource makes my system enter into unsafe state, such resources won't be immediately allocated to that process. Okay, so that is what the use of this safe state is. Anyways, we are going to see examples on calculating even safe state given a number of resources. The same thing is depicted in this diagram, where whenever it is in safe state, there is no deadlock. Whenever system is in unsafe state, there is a possibility. So some part of unsafe state is marked as a deadlock. So we cannot say like if it is in safe state, it is deadlock. No, there is a possibility. Okay. Whereas when system is in safe state, there is no possibility of the deadlock. So that is relation of the state, like safe state, unsafe state, and deadlock state. Now this avoidance algorithm, single instance of resource type is there. We'll make a resource allocation graph that will try to remove the loop. So because we already aware in resource allocation graph, we have processes, we have resources, and assuming that there is a single instance of resource, whenever new request come, it will simply add one edge in my graph, right? And if that results in cycle or loop kind of a thing, then such allocation is not permitted by operating system. That is how to avoid the deadlock. So resource allocation graph is sufficient if for all resource type there is a single instance. So only one resource of that type. Okay. Whereas whenever we have multiple instances of resource type, then we need to go with Banker's algorithm. Okay, so maybe we will go with the Banker's algorithm whenever we need to have multiple instances. Okay. Now the first part is the resource allocation graph scheme. What happens in this is now more mathematically, more technically the same thing is mentioned. Like whatever the edges are there in the resource allocation graph, we know that we already mentioned something like there is resource allocated and there is request for the resource. Okay, so if the edge is from process to resource, that is the request edge. Whenever there is edge from resource to the process, then that is allocation. Now one more type of edge is defined here, and that is called as a claim edge. Okay, and claim edge always go from process to resource. That means that process is claiming that resource. Only just to indicate or to make it different from the request edge, this will be represented by a dashed line. Okay, solid line is not used for that. Dashed line will be used. So the claim edge will be between, or it will be from any process Pi to Rj, ith process and jth resource type, which indicates that the process Pi may request resource Rj, and this will be represented by the dashed line. Now claim edge convert to request edge when a process requests a resource. So first of all, it claim. Okay, it requests that. Now, how it will decide? If that would result into loop or cycle, then only it will be allowed, and then claim age will be converted to request age. So don't get confused between claim age and request age. Request age is like whenever a process requests a resource, but before that we need to check, because this is our algorithm, right? Before that we need to check that if adding this age in my graph will result in deadlock. If it don't result in deadlock, now claim age will be converted to request age. Fine. Next is request age converted to an assignment age when the resource is allocated to the process. So whenever any process makes a request for resource type, and if that resource is available, then this request age will be converted to the assignment. So now 3 types of ages, as I mentioned: claim, request, and assignment. Now only thing is claim age is represented by dashed line, request age solid line from process to resource, and then assignment age is again solid. Of course, the request age and the assignment age both are solid and they are directed. Claim age is also directed. So that is important. So whenever that resource type is assigned to that process, now the direction of arrow will be changed. Previously it was from P to R, that is process to resource. Now this will be from R to P, that is resource to process. When a resource is released by the process, assignment age reconverts to a claim age. So whenever any process release the resource type, then again assignment age will be converted to claim age, changing its direction, changing its style. Okay, and resources must be claimed a priori in the system, because that is what our previous assumption was there. Because for deadlock avoidance, we need some sort of prior information about how many processes are there, how many resource types are there, what are the maximum need of a specific process, what is the maximum number of resource types, and even maximum number of instances of particular resource type is also there. So that prior information is the prerequisite for deadlock avoidance algorithms. Okay, so from this slide, just you need to take 3 things. One thing is, let me try to draw it here. So for example, what I'll do is, this is process, this is a resource. Let me call this as a P, let me call this as a R, that is a resource. So initially what we have is something like this, dash dash. I'll make use of dash, and the arrow is something like this. Now P to R, remember this is the claim age. This is claim age. Okay. Next, if this dash is converted to solid line, then think of this as the request age. And whenever this request is granted, then this will be converted to something like this. This is also solid. Now kindly note the direction of arrow. This is assignment. Resource are assigned to process P. Once process P done with this resource, then process will release that resource. Again, the same age will be converted to the claim age. That is how it works. So claim age, request age, assignment age, 3 types of ages. Any doubt in this? Yes, if anybody has doubt, please post it on chat box. Fine, we'll continue. So for example, now I'll give you few names here. 1, 2, 3, 4. Okay. So I given some numbers to the edges. So two resources are there, R2, and two processes are there, P1 and P2. Now let me put some question on poll. Now the number 1. Now this is which type of age? Claim age, assignment age, or request age? Last 10 seconds. Now see the result. Now the problem is 43% have not responded. 43. Now let me clear one thing. I am continuing with poll, and whoever don't respond, I'll mark it as an absent. Is that clear? I don't know why you are not responding, or maybe I'll add one more thing. I don't know, the fourth option. Okay, so that is fine. Now majority of the student given correct answer, that is the assignment age. Remember, age I just marked as a 1 is from resource 1 to process 1. Remember, it is from resource to the process. That means resource R1 is assigned to P1. So that is assignment age. If you mentioned it as a claim, no, that is wrong. If you are saying it is a request, that is also wrong. So the correct answer is it is assignment age, right? Now let me modify the question. I'll mark it for another. Now answer the same thing. Page number. Last 10 seconds. Now see the result. Now I think you are attendance purpose, right? Because previous poll 40% not responded, this rate to 14%. And right, 53% student given the correct answer. That is number 2 is from P2 to R1. Okay, it is from P2 to R1. Meaning of that is process P2 is requesting for the resource R1. Okay. Now let's check it for age number 4. Third one, type of age. Last 10 seconds. And these are okay. So 73% given correct answer. Still I can see 7 students out of 91 saying it is assignment, where I already mentioned that R1 to P1 is assignment, P2 to R1 is the request, and dotted line is there. And this is really interesting. I need to see the individual results of these students who they are saying it is assignment and request age. Okay, so maybe I'll see the individual results for the students. Anybody is there who want to unmute themselves and talk about why they selected the assignment age? There are 7 students. Why do you think like that? Because I already mentioned it is a solid line. It is not dotted line. Okay. Now only thing is, if it is from resource to process, that is assignment. If it is from process to resource, it is request, and claim is always dotted. It's very simple thing. So 73% student select correct. I still wonder why not 100%. Forget about those who have not given answer. 11 students have not given answer. Okay, fine. So that is how to make use of resource allocation graph. Now looking at this is the unsafe state in resource allocation graph. Now see, for example, the meaning of this. Try to understand the meaning of this graph first of all. There are 2 resources, R1 and R2. There are 2 processes, P1 and P2. R1 is assigned to P1. R2 is assigned to, okay. Now P2 requesting R1, request age, and next thing is P1 is requesting R2, which is shown with the dotted line. Now, if we convert this claim age, now what is the claim age here? It is the age from P1 to R2. This is the claim. If we convert this claim to request, what will happen is this results into loop. This is a perfect condition for circular waiting. P1 holding R1 and waiting for R2, and P2 holding R2 and waiting for R1. So that results in kind of a loop in the graph, resource allocation graph. Okay, so operating system do not allow to conversion of this claim age into request age. Okay. Now, because of that, what will happen is maybe P1 has to surrender the resource R1, for example, because P1 cannot continue without R2. So better option is surrender the resource R1 so that P2 will finish first. Right? So P2 will finish because P2 already has got R2, and because P1 surrendered R1, now that is also available to P2. P2 will utilize R1, R2. It will finish its working execution. Both will be released, and once released, the same P1 will request for R1 also, R2 also, and then P1 will finish. Okay, so that is before entering into the unsafe state, we need to check that whenever we convert the claim age into request age, we need to check whether that age results into loop in graph. Okay. So that presentation, now we do the algorithm. So algorithm is very simple. Suppose that process Pi requests a resource Rj. Request can be granted only if converting the request age to an assignment age does not result in the formation of cycle in resource allocation graph. Okay. The conversion does not result in the formation of cycle. Then and then only we grant the resource. That is what it is. Now, as I mentioned, if there are instances only, then and then it is fine. Whenever we have multiple resources, then we need to go with Banker's algorithm. Okay. So the bullets I mentioned here is Banker's algorithm can be used with multiple instances of resource type. Each process must priorly claim the maximum use. That means a specific resource type required by any process that must be known in advance. Okay. So the maximum use on any specific resource type, that information must be declared priorly. I'm not saying that should be requested there. No, that must be declared. Okay. When a process requests a resource, it may have to wait, even though that resource is free, because maybe assigning that will move or enter the system into a state, right? And that is the reason whenever process requests a resource, it may have to wait for that. If the resource is busy, anyway it has to wait, no doubt. But even the resource is not busy, still processes has to. Okay. And last thing is, when a process gets all its resources, it must return them in a finite amount of time. For example, say 5 different kind of resources required with say multiple instances, those will be allocated. Now that process has to return all the resources to this in finite amount of time. Okay, now why finite amount? Because other processes are waiting for that. Meaning of that is very simple. Whenever resources are allocated to you, you cannot use them forever. Okay, there is a protocol. You should acquire the resource, you should use it, and you should release it. And this release of resources must happen in finite amount of time. It is not forever, right? So these are some assumptions for Banker's algorithm. Now, there are a few data structures used for the Banker's algorithm. And first of all, we'll see whatever the data structures and what is use of that, and then we'll actually see it is moreover like mathematical kind of a thing, but fine, it is making use of some sort of vectors or matrices. Okay, so you think vector as like a one-dimensional array and a matrix as a two-dimensional array to make it very simple. Or whenever you need to implement this Banker's algorithm, say with C++ language or any other language, then whenever the word vector is used in this data structure, that is one-dimensional array, and whenever matrix is used, it is two-dimensional array. That's okay. And for as usual, we'll consider two variables. First of all, n and m, where n is number of processes. So n is attached to the count processes, and m for resource types. It is used for resource types. Okay. Now, very first thing is available. This is important. Now try to understand this. Available. I have short video on this also, but in order to go through that video, first of all, we need to understand the data structures. Okay. Video will take you through one example, solve it. Before that, you need to understand what is use of that data structure. So available is a vector of length m. Now remember, whenever m is used, it deals with resource type and not with processes. Always remember that. So available, it is vector of length m. And meaning of that is how many instances of resource type is available. Okay, so for example, if available of j is equal to k, try to understand this one now. As I mentioned, this vector is of length m. That means it is one-dimensional array wherein m entries will be there. So to make it very simple, whenever I say int a of 10, so a is a vector of length 10. Okay, only thing is in this algorithm it is called as a vector. Why is it called a vector? Because m we are talking in terms of variable and not in terms of fixed. Whereas in C++ language, whenever we talk about array should have a static. So a of int a of 10, it is array. We cannot say int a of b, where b is a variable. We cannot declare array like that. Fine. In C++, it is allowed provided that b is declared before a. That is fine. In that case, we call that a vector. Okay. Just to avoid your confusions, because the word used here is data structures. So because this one-dimensional array is of variable length, it is called as a vector. That's it. That is the only reason. Okay. So because I have, say for example, 50 resource types are there. So available of 50. That is how I'll declare array in C language. Available of 50. Why 50? Because value of em is 50. So that is the resource types. And at any given instance of time, how many units of that resource type is available? Say for example, one of the resource, so available of j. Assume that it is jth resource, and say for example that is a printer, and 5 printers are totally available, out of which maybe 2 are allocated to few processes and 3 are remaining. then it will be written like available of j is equal to, for example, 3. Meaning of this is there are k instances of resource type rj right now available. Okay. Any doubt in this? See, in this Banker's algorithm, very first thing is Banker's algorithm is very important. Second thing is you need to understand first upon data structures and then the algorithm. Okay. Is there any doubt on available? You imagine this like as a balance. Is it okay? Yes, somebody can post it on chat. Is it okay? Or if you have any doubt, those who were not able to respond on poll can post here now. Shubham Jain. Shubham Jain. Shubham Jain is sir. The question is, what is use of available? Shubham, this is question for you. What is use of available data structure? I highlighted on slide. Provide size of vector for resource. See, available vector is used to give the balance of resources. Like for example, how many printers are there that are right now available? Okay. How many files are there? If file is considered as resource. Okay. So available of J, that means it is Rj. J resource is equal to K balance. So that is available. How many resources are available? Okay. So that is first data structure. Second data structure is max. This one. So this matrix is n by m. So n rows and m columns. N rows and m columns. Okay. So if max of ij is equal to k, then process Pi may request at most k instances of resource type Rj. Now this max is, as I mentioned in the previous slide, we need to have prior information about the processes. Like for example, for my process, I need 4 locks. Say mutex lock is one of the resource type. So if I need 4 locks maximum, okay, then these logs can be denoted as RJ and process will be denoted by say PI. So PI process needs maximum of 4 logs. That will be denoted by max of ij equal to k, where I denotes ith process, j denotes jth resource type, and k denotes the maximum demand. Okay, so this matrix will talk about demand by each process for each type. Why I am saying each type? Because it is n by m matrix. So for example, first process just need 3 resources out of 10. If process 1 needs 3 resources out of 10, okay, and the inputs are different, for example, then what will happen is at 10 location where k is 0. That means this process don't need that resource type. And it will be some positive value, like for example k for the required resource types. So available will talk about at this instance of time what is the balance resource. Now for all, of course for all. Max will denote what is the maximum demand by each process for each resource type. Okay. Next is allocation. This allocation is exactly having size of max. It is again n by m. This talks about what is the current allocation of resources for all the processes. So max is maximum demand, allocation is current allocation. Okay. So for example, allocation of I comma j equal to k, meaning of that is currently ith process is allocated k instances of jth resource. Okay, so pi, I is talking with I is for selecting the process, j is for selecting the resource types, and k is something like number, count. So allocation of ij. Once you understand max, understanding allocation is very simple. And similarly, there is called as a need matrix. This is again same like max and allocation, n by m matrix. Okay, so need is what? It's very simple thing. What I need for any particular process, what is the maximum demand, what is the current allocation, and what is the need. Okay, so need can be simply calculated. That formula is given here. It's very simple thing. My max is say for 20. Currently 8 resources are allocated. What is need? It is 20. So whatever my maximum is there minus whatever is allocated is equal to whatever I need. So remaining part. Is there any doubt? Is there any doubt? All 4 available is the max, allocation, and need. These are matrices of size n by m. So always remember the notations used here. Say for example, n is used here, I is used here. They will talk about the processes. M is there and J is there. They will talk about resource types, and quantity is given by K. Quantity is given by K. So whenever I is used, always remember it is ith process. Whenever J is there, always remember it is jth resource type. And the value for I and J will be, like for example, value for I will be always less than equal to n if we start with 1. And if we start it with 0, it is less than n. Most of the time in the book we start with P1, P2, P3, n processes up to Pn. But whenever you want to implement this in, say, for example, C language index array index starts with 0. So in that case, it should be less than n. Okay. Similar is the case for resource types. And whenever you can across J, always remember it is RJ. That means jth resource type. And instances will be denoted by key. That is what the quantity is. Is that okay? Let us move to the next. Now this is the algorithm. 2 more vectors will be taken. They are temporary variables actually. So there is something called as a work and finish. 2 vectors of length m and n respectively. So remember, work is of size m and finish is of size n. So as I already mentioned, because it deals with m, always remember work is utilized for resource types and finish because it works with n. Okay, so finish is for processes. That is the reason I mentioned I, j and m, n. Okay, whenever it is I, it is process. Whenever it is n, it is process. Whenever it is j, it is resource type. Whenever it is m, it is resource type. So work and finish are 2 vectors. Is like as work is equal to available. So whatever the number of resources for each resource type right now available will be copied to the vector work. Okay. There is a question. How n and I both are processes? Okay. See, n is used to specify maximum number of processes in the system. So if there are 10 processes, I can say P1, P2, P3, P4, or P10. So that is what the use of n is. And I is used to select the specific process. So whenever I say pi, it is process. So the variables I and n are related to process. Okay, so is that clear? Similarly, it is j and m. So I is used to represent ith process, j is used to represent jth resource type. Maximum number of processes are denoted by n. Maximum number of resource types are denoted by m. So like n and I both are processes, m and j both are with resource types. Is that clear, Neil Joshi?
Yes, sir.
Yes. Okay. Okay. So okay, let me finish this one. How it is initialized. Finish of I is equal to false. That means actually it is used to hold what are the processes they have finished their work. Okay. Because at the beginning we want to initialize it. Not a single process is finished yet. So all are initialized with false. So it is 0 to, see, as I mentioned, if you start with 1, it is 1 to n. But if you start with 0, it is 0 to n. Okay. So all the processes are marked as not finished yet. That is how we initialize it. Okay, now we'll stop here. We'll continue this algorithm in next lecture.